Swayam Prabha. Digital India. Educated India.
Welcome back everyone, and in this particular module we continue our discussion on the Newton's law and the laws of gravitation, and in particular we are describing how to find the gravitational forces due to uniform objects, right? So along the lines of discussion, let us talk about the gravitation by spheres. Gravitation by spheres, gravitational force due to spheres. Okay. So what we have is, let us consider a sphere. So now we have a sphere, and the sphere now is interacting, sphere of mass capital M is now it is interacting with a point object P of mass small m, and we see that this mass small m. Again, we start by considering an infinitesimally small d capital M and see how this infinitesimally small mass interacts with this point mass small m, right? So the geometry is, let us say this d capital M is subtending a solid angle. Let us say it is subtending a solid angle theta. And let us say that this is at an angle, well, this is at a distance r from my origin O, and further let me also say that the radius of the sphere is a. The radius of the sphere is a, and what we have is that this solid angle mass d capital M is making an angle alpha, right, with the infinitesimal mass d capital M. Okay, so then what we have is, suppose what do we get? So let us now, based on this geometry, start to write the force of gravitation due to this infinitesimally small mass on the point mass, right? So what we have is, we can see that if we look at this particular triangle here, then we see that there are these distances that we have to worry about. So this small r, let us say this, what do we have? Well, I think I have missed one more distance. Let me say that this mass small m, it is at a distance small b, which is the distance from the origin to the Earth's to the sphere's center, right? So that is what we have, the distance of the point mass m from the Earth, from the center of the sphere. So then we see that from this triangle we have that this r, so this particular distance, this one is going to be r cos theta, right? And then what we have is, let's say if this is our capital R, this particular distance, then this particular distance in this triangle is going to be capital R cos alpha, right? So I think now we are ready to write the infinitesimal gravitational force of attraction. We see that the force dFg comes out to be the mass small m times the mass d capital M times 1 over r square, that is the distance between the two masses, and times we have cos alpha because we need to project it along the y axis, and well, again, the x-axis values, they cancel each other. So the net gravitational force of attraction will be only along the y-axis. So this is my y-axis, and let's say we fix an x-axis. Okay. So our x-axis, and similarly we have to fix a z-axis. Okay. So k. So I, j, k. I, j, k. So the direction should be along k. Okay. Okay. So then what we have is that this is also equal to m times dm. So dm is going to be, let's say, the density of the sphere times the volume dv. So dm is going to be the density times dv times r square cos alpha. And notice that my r square from this triangle comes out to be, well, I can finally write down all the other quantities from this geometry and write down the final answer to this. So we have m rho dv times, I think we have missed the constant g here, the gravitational constant, right? And then to find the gravitational force of attraction, we integrate this, and we see that this is going to be integration over the entire volume. So this is going to be m rho. So rho is going to be, well, let me keep this rho. So rho is the total mass of the sphere divided by the total volume, 4/3 pi a cube, right? A being the radius of the sphere. So rho is this, and then we have this distance. So dv. So dv is r sine theta times dr times d theta times d phi, or what do we have? D phi. Yes. So d phi. These are all the solid angles of the sphere, right? And then we have cos alpha by r square. So cos alpha comes out to be b minus r cos alpha. So b minus r cos alpha is divided by r. So divided by r is my cos alpha. That's my cos alpha. Well, something is missing here. So b minus, I don't need alpha here. So this is going to be b minus r cos theta, right? So r cos theta is this particular quantity, and we subtract it from the total distance b, and we are going to get this particular distance, and this particular distance is going to be when divided by capital R is going to be this is going to be my cos alpha, right? And then we also had an r square, so I put r cube here. And finally what we have as the integral is my r is from 0 to a, and my theta is from 0 to 2 pi, and my phi is from 0 to pi, and then everything else is m times rho times what else? Times g times dv. So dv is r sine theta times dr d theta d phi divided by times b minus r cos theta divided by r cube, and r cube is going to be r square plus b square minus br cos 2br cos theta to the power 3/2. 2br cos theta to the power 3/2. And that is the complete integral that we have to perform. And then later on, when we see that after we perform this integration, we find that the answer is m capital M g by b square. So that is the total gravitational force. Surprisingly very simple answer. And if we look at this answer very carefully, we see that the answer comes out as if we have assumed the sphere having a mass which is concentrated at the center of the sphere O, right? We have taken a uniform sphere, by the way. What do we mean by uniform sphere? Its density is constant. That is uniform sphere. If its density depends on the angle and the distance, then it is a non-uniform sphere. So for a uniform sphere, we find that the gravitational force is surprisingly simple, right? So let me write down this statement that I just made. Spheres attracted by other spheres. Well, what has happened? So the statement I am trying to make is spheres either attracted by, let's say, point masses, that is the example that I just saw, point masses, or by other uniform spheres, everything is uniform here, right? So uniform spheres, I should also add the word uniform here. Uniform spheres either attracted by point masses or uniform spheres altogether is going to have a gravitational force, will be attracted with a gravitational force symmetrically behaving, well, will have a gravitational force as if the spheres were point masses with mass concentrated in its center, right? So that is a simple rule that we have seen for symmetric spheres. Okay, so then let me now wrap up this particular discussion by introducing the so-called principle of equivalence, and from there I am going to talk about the so-called acceleration due to gravity, right? So what is my principle of equivalence? The principle of equivalence says that the normal mass of an object is also equal to the gravitational mass, right? So principle of equivalence, it says that the inertial mass is it is identically equal to the gravitational mass. The inertial mass is identically equal to the gravitational mass. What do we mean by inertial mass? Inertial mass, the definition of inertial mass comes from the Newton's first law. That is, the inertial mass is the reluctance of the object to be influenced by any external forces, or it is some sort of a resistance by the object due to the external force, right? So that comes from the first law. And gravitational mass is the second property of the particle which determines the gravitational force, the G force, right? And the principle of equivalence says that both masses are equal, and from here I can find my acceleration due to gravity, the constant g, small g, right? So let me talk about from this principle of equivalence. Okay, so what is my gravitational acceleration g? So it says that suppose you have a particle p of mass capital M, and it is attracted by a system of particles. So we have a particle of mass capital M, right? Let's say particle of mass capital M, let me say particle P. So here we have a particle P, and it is being attracted by lots and lots of masses of small mass Mi, right? So we can quickly write the total interactive forces. The total interactive forces of the system is m times m1 times g divided by r1 square. Well, r1 is the interaction distance, and let me call this as this direction as e1, right? So this is the direction e1, and similarly we can write so on. If there are n number of particles, n particles of masses mi's, I can write this as the sum of n terms as follows. So this is m times small mn times g divided by rn square times en, right? And then from here I can take this common thing out. So this is m times summation mi times g divided by ri square ei, right? So this is my net sum of the forces, and we see that this force is due to the inertia. So this particular force is also due to the inertia of the masses mi's. So this is the inertial force, right? The force measured in the inertial frame of reference. And we saw that this is also equal to the gravitational force. Well, of course, we are talking about the gravitational law of attraction. Now, if that is the case, then the inertial masses should also be equal to the gravitational mass from the law of equivalence, which means that when you have an inertial force, the force is always mass times acceleration. So this is my acceleration. Due to the gravitational force, and I call this acceleration and I give it a constant g. The g will be a vector because it is the sum of vectors, right? And hence we have arrived at the universal constant, that is the acceleration due to gravity. Okay, so then so what do we have? So typically this acceleration due to gravity acts along a direction which is directed towards the center of the earth. So suppose here is my earth, and let's say here is where I am sitting. My gravitational force of attraction is going to act downward towards the center of the earth, right? So let me call this vertical direction, the upward vertical direction, as my k hat direction or the z direction, and then my g comes out to be g times minus of k, right? So it is a downward vertical direction velocity, acceleration vector. Okay, so typical values is at sea level. The value of g is roughly 9.8 meters per second square. These are all measured values, and typically at r equal to at a distance of 6400 kilometer. What is the significance of this distance? This distance is the radius of the earth. So if you are at double the radius of the earth from the center of the earth, which means that here you are at a distance r and you are again at a distance r. So this is 2r. Right, so it at r, so r from the surface of the earth, then g comes out to be roughly 1/4 of the g at the surface, right? So let me call this sea level g as gs, and then at r g is equal to gs by 4, right? And then at moon my g comes out to be gs over 6. So 1/6 the acceleration due to gravity, and typically the weight also reduces by 1/6. It gives a 16% of the original weight of the person that is measured on the earth. Okay, so enough of all these basic data. Let me just look at some examples as to how to apply these issues, these concepts in real life examples. So let me talk about the concept of the so-called weightlessness. So what do we have? We have, let us look at an example. So in this example, I am trying to explain the issue of the so-called weightlessness. Okay, that is, how come a body of mass m will not experience any weight at all? It all depends upon the frame of reference we are talking. So suppose we have an elevator, right? So let me draw an elevator. So suppose we have an elevator, and it is, of course, when elevator works, it moves up and down using a cable, right? So suppose at t equal to 0, we cut the cable. Well, that should not happen in real life. That is a very scary situation. But otherwise, suppose, let us look at this case that we cut the cable at t equal to 0. We cut the cable, so this elevator is going to fall down because of its weight, right? This question is, suppose we have a person which is sitting in that elevator, or let's say standing in that elevator. We have to figure out what is the acceleration of this person with respect to this elevator, right? So this question is, so let me write down this problem. So at t equal to 0, we cut the cable of the elevator, and all contents of the elevator falls under uniform gravity. Okay. So this question is, what is the motion? We have to describe the motion. What is the motion of the particle with respect to the elevator? What is the motion of the particle with respect to the elevator, right? So in the frame of the reference of the elevator. So what we have got is, so suppose we have, let me now fix the frame of reference here. So let me say we have one frame of reference which is fixed. So we have a fixed reference frame. So let's see, let me call this as F with ij. So ij, well, this is not going to be j here. So ij, so let me call this as I, this as j, and this is k. So ijk, this is a fixed frame of reference, and we fix another frame of reference with respect to the moving elevator, right? In such a way, so let me just draw all this. So let me call this as f prime. So we have f as the fixed frame, f as my fixed frame, right? And f prime as my moving frame. So f is my fixed frame and f prime is my moving frame, and we see that we have set up the two frames such that f prime is not accelerated. Well, it's not accelerated with respect to the fixed frame, right? So what does this statement means? That look, both frames, both the elevator and the frame f prime, they are getting accelerated. Once you cut the cable, they are going to fall and they will experience an acceleration g, right? But with respect to with respect to there, what is the statement here? That relative the acceleration with respect to the fixed frame, the statement is, that we have that there is no net acceleration with respect to f prime. Okay. So let me just show this issue step by step. So we have the two frames, fixed frame and the moving frame, and suppose suppose this particle, I call this as particle, although this is a person. Suppose this particle P has mass m, right? This has mass m, the inertial mass, and then relative to with respect to the fixed frame, with respect to the frame F, the fixed frame, with respect to the fixed frame, this frame, the particle m, so m is moving, or I would say accelerating with acceleration with accelerating with force minus mg and towards the downward direction, right? So this particle is moving downward direction. So that is the motion in the fixed frame, right? And then we have to figure out what is the acceleration of this particle or this mass particle of mass m with respect to the moving frame, right? So we have to figure out the acceleration a bar prime with respect to the frame f prime. That is, what is the acceleration of this particle in the moving frame, right? So we see that it turns out that the formula that we have is that the total acceleration with respect to the fixed frame, so this is my acceleration in the fixed frame, is equal to the acceleration in the moving frame plus the acceleration of the frame itself. So if this frame f prime, so that is what I wanted to say. So if f prime is moving with respect to f with acceleration a, right? That is, the elevator is falling with respect to the fixed frame with an acceleration capital A, then we have that the acceleration of the object in the fixed frame is equal to the moving acceleration plus the acceleration of the frame. So now this is going to be minus g k hat because of this quantity, and this is going to be a prime, and the acceleration of the frame is also moving with minus g k hat, right? Because the frame is also falling with the same acceleration due to gravity. So from here we see that a bar prime comes out to be 0, or that the acceleration of this particle in this moving frame is 0, which means that the weight of the particle p in f prime is going to be m times a prime. This is going to be 0. So in the moving frame the particle has no weight, and that is what I meant by saying weightlessness. So when you have this setup where the frame itself is accelerating with the acceleration due to gravity, the particles are literally going to start to fly, or they are not going to experience any weight at all. Okay, so let us wrap up our discussion at this point of time, and in the next discussion, in the next lecture or in the next module, we are going to continue our topic on particle dynamics. Namely, we will cover more intricate, more interesting examples of the gravitational force. So thank you so far for listening.